National Aeronautics and Space Administration's New Horizons space probe began its mission back in 2006. Since then, it has gathered a huge amount of valuable data for us, including photographs of Jupiter and its moons. However, when it reached Pluto in 2015, it exceeded even the boldest expectations. New Horizons got close enough to take high-quality images. Scientists are still processing the data from that mission. At the same time, the probe made scientists think, do we really know what Pluto is like? Is it truly a barren, cold dwarf planet? Is there an ocean of liquid water beneath Pluto's surface? And why are there icy dunes on the planet's surface? The main goal of the New Horizons mission was to study Pluto. At that time, it was still considered a planet, and we couldn't yet observe its surface up close. The journey to Pluto is long, so they had to find ways for New Horizons to reach its destination faster. So about 9 hours after launch, the probe reached the moon's orbit. New Horizons flew past other planets in the solar system. It sent us images of Jupiter and its moons. But most importantly, while at a distance of 2.3 million kilometers from the gas giant, New Horizons came under the influence of the planet's gravity. This helped shorten the travel time to Pluto. Originally, the journey would have taken 14 years, but this way, it was reduced to 9. However, the journey was still a long one, so for a while, the spacecraft was put into power-saving mode, into a so-called hibernation state. This was done to check if all the components were working properly. Unfortunately, technical problems could not be avoided. At that time, New Horizons was 5 billion kilometers away from Earth. It was also at a huge distance from the Sun. Accordingly, the spacecraft was not receiving enough solar energy. This led to communication problems. The situation did not improve as the probe kept moving farther and farther away. The signal began to reach us with a significant delay. However, there were also positive moments. As New Horizons approached Pluto, the level of detail in the images it took increased. At that time, the spacecraft discovered 2 previously unknown moons of Pluto, Styx and Kerberos, or Kerbers for short. This gave reason to believe that the dwarf planet might have more undiscovered moons, as well as a greater amount of space dust and rocks. Initially, it was believed that there were much fewer of them. This fact posed an additional threat to New Horizons. The spacecraft could have failed because of, say, space dust. It was possible to use the spacecraft's antenna as a protective shield. However, there was another option: to fly closer to the dwarf planet than scientists had originally planned. That way, it was possible to enter an area with less dust and rock fragments. The scientists chose this option, but the difficulties didn't end there. 10 days before the closest approach to Pluto, contact with the spacecraft was lost. Fortunately, the scientists were lucky. They were able to fix the problem since it was a system overload. Some important data was extracted as a precaution in case something irreversible happened to New Horizons. On July 15, 2015, New Horizons reported to Earth that the maneuver had been successfully completed. After approaching the dwarf planet at a distance of 7,800 kilometers, it took hundreds of images and also studied its atmosphere. The spacecraft did an excellent job. Here is Charon, one of Pluto's moons, the dwarf planet itself from different angles, and of course, the famous heart-shaped spot on Pluto. However, all this data was sent to Earth at a speed of 1 to 2 kilobits per second. It took 15 months to transmit 6.25 gigabytes. Despite all the difficulties, we received truly unique data. The wait was worth it. We were able to learn more about the mountainous terrain of the dwarf planet. We found out that there are peaks that reach 3,500 meters in height. There are also icy mountain ranges. It is assumed that they are no more than 100 million years old. This gives reason to believe that geological processes have taken place on the dwarf planet relatively recently. It's also interesting to look at Pluto's atmosphere. You can see a layer of haze 200 kilometers above the surface. It forms as a result of methane breaking down under the influence of ultraviolet radiation. Other gases, such as acetylene and ethylene, are then produced. These gases turn into icy haze in the colder regions of the atmosphere. The influence of the atmosphere on Pluto is significant. For example, the red-colored regions formed under the influence of gaseous hydrocarbons near such a huge red area on the plane of the satellite is Pluto's famous heart, the Tombaugh region. It is a massive glacier made mostly of nitrogen. We don't know very much about this region. We also don't know its origin. It's possible that the glacier formed at the site of an impact crater. Interestingly, on Pluto, ice immediately turns into a gaseous state. This is called sublimation. The temperature simply doesn't allow the ice to melt and become liquid. On the surface of the glacier, it was noticed that the nitrogen ice there takes the shape of geometric figures. Why does this happen? It may be the result not only of the sublimation process, but also of the uneven distribution of ice. Scientists also have questions about the location of the satellite's plane. There is a theory that this area shifted in the past. This process is called polar wandering. If this is true, this area could affect Pluto's rotation. Some gravitational anomalies are observed in Pluto's heart. It's similar to attaching something massive to one side of a round object. So what gives the satellite's plane such significant mass? There is a suggestion that there is an internal ocean beneath it. And this makes sense since New Horizons discovered signs of recent tectonic activity, which could be an indirect sign that an ocean once existed. After determining the approximate density of the dwarf planet, scientists found that beneath Pluto's surface there could be a layer of molten sticky material, similar in structure to tar. Most likely, it was originally some kind of organic substance, probably carbon. However, under the influence of pressure and temperature, the substance changed its properties. This layer could be up to 100 kilometers thick and partially mix with the underground ocean. But if there is an underground ocean on Pluto, then why hasn't the water frozen there? The dwarf planet formed from cosmic dust, rocks, and ice that gradually accumulated in one place. When Pluto formed as a planet, the heat generated in the process could have melted fragments of ice. However, this theory only works if heat was actually released during the formation process. As you know, when water freezes, it expands, which leads to cracks forming on the surface. This would have happened if Pluto's beginning was hot. If, on the contrary, the beginning was cold, then compression would have occurred on the surface. In these images provided to us by New Horizons, we see rather old craters, but there are no signs of compression on them. There is a suggestion that there may be a large amount of ammonia in the underground ocean. Ammonia has no color, but it does have a specific smell. What's interesting is that when ammonia reacts chemically with water, it keeps its temperature higher than it otherwise could be. If this is true, then there could be an internal ocean on other planets in the solar system as well. Whether this is the case, we will definitely find out in the future. New Horizons in general made more than 200 scientific observations, which included not only Pluto itself, but also its moons. Now the spacecraft is traveling through the Kuiper Belt. New Horizons has opened up not only new possibilities for us, but it also presented us with many new challenges. Have you ever wondered what the universe looked like in its early stages? Surely everything was different right after the Big Bang. However, the James Webb telescope looked deep into the universe and found out that its early version was in many ways similar to what it is today. Surprisingly, we see all its components already formed, interacting with each other as they should. How will this fact affect modern space science? How does it change our understanding of the universe? Take a look at this image from the James Webb telescope. Here we can observe galaxies that are so old, Their age doesn't fit into the usual model of the world, and this fact could completely change our understanding of how the universe is structured. Now, scientists need to find a way to explain the data they've received. At first, there was a theory that the telescope's mechanisms were not perfect, that there were some flaws. However, after verification, this was not confirmed. Soon it was found that the age of the galaxies matches previous calculations. It's possible that in the image, we are not seeing the galaxies themselves, but some other structures. Looking at all the data we have at our disposal, it seems very likely that it is actually our understanding of how the Big Bang happened is not entirely correct. So, scientists suggest that these galaxies, as fully developed structures, were already functioning about 13.6 billion years ago. However, there is one catch. The thing is, almost 14 billion years ago, there were the so-called dark ages, when there shouldn't have been any galaxies at all. And we're not dealing with simpler, recently formed objects, like small star clusters, but with huge galaxies. Moreover, such structures are more typical for the universe at its current stage of existence. It turns out they appeared much earlier than we could have imagined. Some scientists believe that this is actually not an exception to the rule at all. They are confident that with further research, we will encounter more and more similar objects. Right now, science is experiencing something like an astronomical crisis. Many of our ideas about space may turn out to be not very accurate, and this will affect all of science. It may turn out that we do not live in the kind of world we imagine. Even though in the image from the James Webb telescope, we see only a small part of the universe at its early stages, the data we have still gives us reason to believe that it was almost as developed then as it is now. Most scientists once thought our lack of knowledge about star development was the main issue, but this idea is now widely dismissed. Telescope data sped up this shift. As we explore further into the universe, we may find we're not dealing with protostars or similar objects at all. We will be facing structurally complex objects. At the moment, scientists have more and more evidence for this. Some of them have already found evidence that there are galaxies in the universe with significant redshift. So significant that it could be proof that such galaxies appeared almost immediately after the Big Bang. And here, all of cosmic science faces a much more important question. Was there even a Big Bang at all? And can we even claim that the universe has a beginning? And this brings up a number of additional questions. For example, what is the shape of the universe? Is it infinite space? Is it a closed space? Could it be that all these years we've been missing some important detail without which we couldn't put together a complete picture? In fact, revising old knowledge in the science of space is absolutely normal. Joel Ledger from the University of Pennsylvania, together with his colleagues, conducted a detailed analysis of light signals coming from older galaxies that appear in images from James Webb. During the research, it was important, so to speak, to break down the signals into separate components in order to find out which element was dominant at which period of time. Another important aspect is the composition of the galaxies being studied. If we are talking about the early universe, light elements like hydrogen and helium mainly prevailed there. At later stages, heavy elements appeared, nitrogen, carbon, and others. This is exactly what contributed to the formation of galaxies as we see them today. However, we found out that such elements were already present in old galaxies. Moreover, we are now analyzing the light radiation that came from galaxies aged between 4 and 8 billion years. It turns out that we have more and more evidence that the formation of galaxies began even before the Big Bang. Can we explain this by saying that we were initially mistaken about the period when the Big Bang happened? It might seem like a simple and at first glance logical explanation. However, we should take into account the fact that all facts about the universe are closely interconnected. If we change one fact, we would have to change many others as well. It's like a house of cards. If you remove one card, the rest will collapse. A lot depends on actual observations at this stage. and not all processes can be recorded due to the insufficient technological level of our science. So the question is quite complex. Unfortunately, there is no simple explanation here. There's another important detail to mention. The early galaxies we see in telescope images don't have clear outlines. We see something that looks like a large spot of light. To conduct the most thorough analysis of the image, scientists use special programs. This is necessary to understand whether we're really dealing with a galaxy or, for example, just the accretion disk of a black hole. Interpretations of certain facts are not always accurate. For example, once the American astronomer Edwin Hubble, after whom the famous telescope was named, observed galaxies and discovered that constant expansion is characteristic of the universe. His observations also influenced the research of the astronomer Alan Guth, who, in the 1980s, proposed the theory of cosmic inflation. It was assumed that it was precisely due to the process of inflation that cosmic space became mostly homogeneous. However, over time, we have become convinced that the universe is not as homogeneous as previously thought. Perhaps Edwin Hubble simply misinterpreted the data he received, or perhaps he was just missing some important piece of the puzzle for a complete picture. It's incredible that now we have the opportunity to literally lift the veil on the universe's past. We can process light signals that are as old as 13.7 billion years. James Webb, and not only him, will be able to study even earlier periods of the universe in the future. Then perhaps most phenomena will finally find their explanation. It's like a real journey through time. With new knowledge, we may be able to expand our understanding of the very nature of time and space. Perhaps new theories will emerge that explain phenomena that previously seemed incomprehensible. This also opens up new opportunities for research in cosmology and astrophysics. And it may turn out that soon humanity will be able to integrate new technologies into space science, and the process of exploring the universe's past will move even faster. Such possibilities are inspiring and excite curious minds. But they also hint at the need for vigilance and caution in interpreting the data obtained. When we explore the depths of the universe, we encounter a number of important questions. How do we deal with contradictions to the fundamental laws of classical physics? What properties of matter and energy exist at different levels, including the microscopic? Quantum physics helps us with these questions. Let's look at some examples of how the universe works. Let's find out if it's true that it turns our understanding of the world upside down. And what would you say if I told you that objects can be in two places at the same time? There is a hypothesis that a quantum object can exist in several states at the same time. That is, at the same moment, there are two versions of the same object. And when we study such objects, we can't say exactly where one of them will be after some time. We can only make assumptions, and we can only know the probability when we take the wave function into account. This is a complex function that helps determine the state of a quantum system. An object exists in two states at the same time until we find out which state it is actually in. A classic example of this phenomenon is the famous situation with Schrödinger's cat, which is either dead or alive. We know that the cat exists in space, but is it alive or dead? Question? It's like multiverses in comics. Many also call this a multiverse in a quantum system. There's a fairly common opinion that an object does not transition from one state to another. We're simply dealing with two versions of the system. If this version is true, then we don't need to choose which state is real, and we don't need to know when the object will transition to another state. Let's move on to wave-particle duality. What is it exactly? It's a hypothesis that was proposed by the French physicist Louis de Broglie. The essence of it is that every elementary particle has wave properties. At the same time, waves also have particle properties. In this way, objects of matter sometimes display the properties of particles and sometimes the properties of waves. Let's take light as an example. Sometimes we consider it as a collection of photons, that is, particles, and in some cases we talk about it as electromagnetic waves. Photons are especially important for us because they can become real helpers in the space industry. For example, with their help, we can launch spacecraft by creating special solar sails that set objects in motion. However, we know that a photon is a massless particle. So how will solar sails work then? Yes, a photon has no so-called rest mass, but we can determine its momentum because we know its energy value. When light pulses are transmitted, pressure can be exerted on certain objects, although such a phenomenon is difficult to detect in space because the effect on massive objects is insignificant. Since we can consider light both as a collection of particles and as waves, the explanation for impulses and pressure can also be different. If we are talking about the wave approach, then, when interacting with charged particles of an object, the waves are reflected and transfer part of their energy. If we are talking about photons, when they collide with the particles of a body, they also transfer part of their energy to them. As you can see, the result is the same in both cases. Quantum physics plays a huge role in studying the nature of black holes, or more precisely, how they disappear. Here we will talk about Heisenberg's uncertainty principle. Its essence is this: we cannot simultaneously determine the exact speed, momentum, and exact position of an object. The more precisely you know one of the values, the more uncertain the information about the other becomes. Stephen Hawking suggested that this principle also applies to black holes. Such processes occur at the edge of these objects. One particle leaves the boundaries of the object as radiation, while at the same time the black hole itself absorbs the other particle. The radiation becomes more and more intense, which leads to the gradual shrinking of the event horizon. And, according to Hawking, the black hole loses mass to such an extent that it simply evaporates. To study celestial bodies, we also cannot do without quantum physics. Let's talk about energy levels. The point is that they represent the size of the electron's orbit, and the size is predetermined. If the level increases, the electron compensates for the size of the orbit by absorbing a light particle. If the situation is the opposite, meaning the electron moves to a lower energy level, it simply emits a photon. In this way, the size of the orbit decreases. How does this help us in studying stars? When we look at the light of a particular star as a spectrum, we see the colors that are missing. This helps us determine the composition of a specific celestial body. Our main star, the Sun, also cannot do without quantum physics. Two protons, which have positive charges, collide with each other, but they immediately repel each other. The so-called Coulomb barrier arises, which serves as an obstacle for protons. They can't move further, just as they can't enter the atomic nucleus. In this case, nuclear fusion simply cannot occur. But if we talk about waves here, the situation changes dramatically. The proton can now break through the barrier. This is what we call the tunneling effect. It occurs when the total energy of a particle, for example a proton, is less than the height of the barrier. The paradox is that this seems to contradict the law of conservation of energy for particles. However, as we see, in quantum physics, this turns out to be possible. This process is especially important for us, because if thermonuclear fusion disappeared, the Sun would also begin to fade. It would shrink in size while its density would increase. This would trigger the Pauli exclusion principle. According to it, certain particles, called fermions, cannot be in the same quantum state at the same time. Gravity can push particles toward this, which causes resistance. All of this leads to the formation of white dwarfs. You might find it hard to believe, but quantum physics also intersects with biology. Scientists at Oldenburg University conducted an experiment to find out how birds respond to magnetic fields. According to one theory, a special protein called cryptochrome helps them navigate using the magnetic field. It is located in the retina and is light sensitive. The amount of cryptochromes changes depending on the time of day. The exception is the protein cry4. Its amount increases when it is time for birds to migrate. For their research, scientists use chickens, pigeons, and also robins. Robins are migratory birds that travel a long distance to reach Africa, where they spend the winter. In robins, when exposed to light, cryptochrome produces radical electrons, which causes strong sensitivity to the magnetic field. In the bird's brain, something like a map of the magnetic field appears, where the poles are marked as small red spots. At this stage, we can talk about a quantum mechanical magnetic sense in birds, although of course this aspect requires further research. Quantum physics is a complex, sometimes overly theoretical, but incredibly useful science for us. As we can see, its benefits can go far beyond space. Quantum physics pushes us toward new discoveries. We expand our understanding of the universe, which will help us lift the veil on seemingly eternal mysteries. Do any modern people still believe the Earth sits on 3 elephants and a giant turtle? Maybe someone still sees a crystal, unmoving dome in the sky? Are such intellectual dinosaurs still around? Aside from stubborn flat earthers, these beliefs likely vanished centuries ago. However, anyone who firmly believes that our current knowledge is far removed from the ideas of ancient astrologers is deeply mistaken. The latest discoveries in astronomy only confirm the inconsistency of our theories, which several generations of scientists have believed in. The surprises started a long time ago, but in 2021 a discovery emerged that undermined the very foundation of our understanding of the world. So, what exactly was discovered then? A gigantic arc of galaxies, which far exceeded the Sloan Great Wall in size. And for a long time, this object, by the way, was considered one of the largest ever discovered in the universe. The Sloan Great Wall stretches for 1.37 billion light years, while the arc of galaxies discovered in 2021 is 3.3 billion light years long, or 1,000 megaparsecs. But that's impossible, the scientists exclaimed in unison. Why is it impossible? Let's figure it out. It's all about homogeneity, which according to widely accepted theories should be present in the macrocosm at great distances. That is, there shouldn't be any noticeable and such large structures in the macrocosm, but they exist, and it's impossible to ignore this fact. The galaxy arc, if we could see it without a telescope, would appear 20 times larger than the moon in our sky. Debates about this object's origin and even its existence were still ongoing when, in early 2024, University of Central Lancashire researchers discovered another remarkable structure. As before, graduate student Alexia Lopez did this in the same part of the sky near the constellation Boötes. This time, it was about a ring of galaxies with a diameter of about 1.3 billion light years, located 9 billion light years away from us. If we use the same analogy as with the arch, then to the naked eye in our sky, this ring would look like 15 full moons. So what's wrong with the discovered structures? To repeat, the cosmological principle tells us that matter in the universe must be distributed uniformly. So at great distances, we shouldn't observe any colossal structures. Here's an example. If you're in a forest or near it, you'll see individual trees and other objects, but if you fly over the jungle in an airplane, it will just look like a uniform green spot. It's exactly the same in the universe, only the scale is billions of times larger. Do you think this is the only oddity that appeared after the discovery of the Ring of Galaxies? Not at all. The thing is, when we talk about an object that's 9.2 billion light years away from us, we often assume that we're seeing it as it was after that amount of time had passed. However, with great distances, things change. We must consider the universe's constant expansion. So the Ring of Galaxies is likely even older, which is also unlikely. Such structures simply couldn't have formed in the young universe. So, does that mean astrophysicists and other scientists have just been wrong all this time? Otherwise, why don't these objects fit into any of the generally accepted cosmological theories? After all, it's practically impossible to explain their appearance. But scientists still took on this thankless task. And here's what they managed to find out. Hypothesis 1, part of a megastructure. As already mentioned, both ultra-giant structures are relatively close to each other. if you can use such an expression for monstrous cosmic scales. Astronomers found them while analyzing the light from quasars absorbed by galaxies that are part of these structures. Using the Sloan Digital Sky Survey wide-angle optical telescope, a three-dimensional map was created and statistical algorithms were applied, which led to the discovery of these objects. So some scientists have made a bold suggestion that both structures could be part of something even more global. Something that we are not yet able to see or comprehend. It's frightening to imagine what the purpose of this colossal conglomerate might be. After all, it's much larger than even our boldest ideas of a Dyson sphere or other similar structures. Second hypothesis, VAO. Its supporters believe that the appearance of the arc and the ring was caused by baryon acoustic oscillations. What is that? To put it simply, it's a kind of ripple caused by the activity and fluctuations of the early universe. In its youth, it was an extremely inhospitable place. Yes, if you think it's deadly for an unprotected person now, you can't imagine what the universe was like right after its birth. It was literally a soup of boiling plasma. There couldn't have been any stars, planets, or other objects at that time. Or we're complete losers, and all this time we've believed in a bubble, just like ancient people worshipped a giant turtle and elephants. However, we've gotten sidetracked. The Sloan telescope also studies the distribution of matter over large distances, so its data was used as the basis. According to some theories, gravitational interactions with waves of the primordial plasma, the newborn macrocosm, created so-called waves in space. Again, imagine in your mind a soup just starting to boil. These waves formed certain bubble-like structures, or so-called spherical shells, which are denser than the rest of space. Continuing with culinary analogies, you can think of it like jelly that wasn't stirred in time, resulting in lumps forming. Here's the issue. The large ring looks more like a two-dimensional spiral than a bubble or sphere. The giant spring is positioned so we see it as a ring. Secondly, both the ring and the arc are much larger than the theoretically possible bubbles of baryonic matter. That's why the already weakly supported theory of baryonic acoustic oscillations doesn't hold up as an explanation for the appearance of colossal structures. Hypothesis 3, the cyclicity of the universe. Once, British physicist Roger Penrose and his colleague from the Center for Cosmology at the Yerevan Institute of Physics, von Gurzadjian, proposed the existence of a cosmological model within the framework of general relativity, in which the universe goes through endless cycles and tends toward a singularity, only to be reborn again as a result of the Big Bang. How does this happen? According to the aforementioned scientists, the universe is born, lives, and expands endlessly. This process continues until there is no matter left in space and scale, loses its former meaning. After that, the completely empty universe turns into a singularity, which once again triggers the cycles of world creation. So, that very umbilical cord, or rather the scars from it, we saw using a three-dimensional map created by the Sloan telescope. The scale of the ring arc fits this definition exactly. Sounds logical, doesn't it? Hypothesis number 4, string theory. Here we mean topological defects of matter which theoretically appeared during phase transitions in the early universe. That is, essentially these are some creases and bends like on crumpled fabric. Therefore, it is quite possible that the arc and the ring of galaxies are precisely the result of the universe transforming from one stage to another. However, this is only a theory since so far no clear evidence has been found that such strings actually exist. What does this imply? It seems that scientists will have to reconsider the fundamental principles of cosmology, as there are more and more reasons for this. For example, there's the already mentioned Sloan Great Wall, or the South Pole Wall, which is 1.4 billion light years across, or the largest structure ever found by astronomers, the Hercules Corona Borealis Great Wall, which is about 10 billion light years in size. All of these structures challenge the traditionally established cosmological principle, forcing scientists to feel uneasy as they search for explanations for this obvious discrepancy. Moreover, the Hercules Corona Borealis Great Wall violates several other principles that astronomers have firmly believed in. Since its distance is 10 billion light years, it means we see this structure as it was 10 billion years ago, not taking into account the expansion of the universe that was mentioned earlier. That is about 3.8 billion years after the Big Bang. But the current model of evolution does not allow for the formation of massive structures at this stage in time. That is, almost all the castles built by scientists during this time are beginning to gradually collapse. Astronomers still can't even imagine how to explain the appearance of such monstrous walls, arches, and rings from a scientific point of view. It's as if the universe is preparing us for something, trying to tell us something important, but we don't understand its hints. Perhaps ahead of us lies the emergence of an entirely new physics, radically different from the one whose postulates we follow now. The thing is, no matter how hard scientists try, they very often apply the laws that work on Earth to objects that are not only beyond our limited world, but also beyond our understanding. Probably from the perspective of someone who knows the truth, we look like ants swarming over an apple, unaware of what it really is. A recent discovery feels like a bottle of Coca-Cola dropped from a plane into a bushman's hands. Just like in the movie, The Gods Must Be Crazy. That is, we see everything, but we can't really explain it. When night falls, the sky is quiet and cloudless. We can lie on the grass and watch thousands of stars above. It seems like there are already too many of them, but that's not all. Many celestial bodies can't be seen with the naked eye. For that, we need telescopes. They open up new frontiers for us. Thanks to them, we have the opportunity to observe billions more stars. In our galaxy, the Milky Way alone, their number reaches from 100 to 400 billion. Just imagine how many there are in other galaxies. How many celestial bodies the universe contains. Stars come in different types, including different sizes. Take our sun, for example. You would probably call this star huge, but compared to other stars in the universe, it's not that big. So how huge can stars be? Which star is currently considered the largest? Before we move on to our discussion, we need to understand what we mean by the largest star. Are we talking about volume or mass? And what exactly is the volume of a star? That's the space occupied by the star. And what is the mass of a star? It's the amount of matter contained within the star. We notice an interesting trend. More massive stars are smaller, while stars with larger volumes have less mass. The older a star gets, the more mass it loses, and it often increases in volume. The most obvious example is our sun. It's aging, and sooner or later, more precisely, in about 5 billion years, it will use up all its nuclear fuel. Then the sun will begin to increase in size and will engulf the orbits of the planets closest to it. Among the engulfed planets could be Mercury, Venus, and even Earth. That's why we need to understand by which parameters we determine the largest star. Let's talk about the most massive star known to us. It is called BAT 9998 and is located in the Large Magellanic Cloud Galaxy. And this star, just think about it, is 226 times more massive than the Sun. We don't know much about its origin. However, there is a theory that it's simply two different stars that merged into one at some point. Perhaps this is the reason why BAT 9998 is so massive. The star is quite young. Scientists estimate its age to be 7.5 million years. For comparison, the age of our sun is 4.6 billion years. BAT 9998, like other stars, is rapidly losing mass. Most likely, after some time, there will only be a black hole in its place. As you can imagine, BAT 9998 does not hold the title of the largest star. Surely, if you have ever wondered which star is the largest in size, you have come across information that it is the red supergiant UY Scuti in the constellation Scutum. It appears at the top of Google search results, where you probably looked for the answer to this question. It was first thought the star was 1,700 times bigger than our Sun. This is what gave Scooty the status of the largest star in the universe. However, after several years of additional research, it turned out that the star is only 775 times larger than the Sun. Scooty is still a rather large star, but it's far from the largest. Moreover, it no longer even makes the top 10 largest stars. So which star holds the record now? Actually, it's not that simple. A few years ago, a red supergiant called Stephenson 218 was widely discussed. It's located in our Milky Way galaxy in the Stephenson 2 cluster. According to scientists' estimates, it could be so huge that it would take up almost the entire solar system. To completely circle such a star, it would take us 9 hours if we were traveling at the speed of light. Meanwhile, if we were flying around a planet from our system, the flight time would be measured in seconds. Scientists who allow for the existence of such a star suggest that it is 2,150 times larger than the Sun. The information about Stephenson 218 is rather vague. Opponents of this theory argue that it contradicts the theory of stellar evolution. They believe that there is a certain limit for stars that prevents them from growing any larger. It is assumed that a star cannot be about 1,500 times larger than the Sun. Distorted results for Stephenson 218 and Scooty occurred because scientists first misidentified their approximate locations. The discrepancy was too great, so the pieces didn't fit together. Although it's worth remembering that the theory of stellar evolution is still just a theory, we still can't say for sure how large a star can grow. Many factors can influence this. Both certain features of evolution and the composition of the star itself play a role. In general, determining the size of huge stars is very difficult because the outer atmosphere of potentially giant stars can expand so much that it simply merges with the interstellar medium. That is, in this case, it's hard to tell where the boundary of the star is, and the difficulties don't end there. Usually, such massive stars are not only very bright, but also surrounded by a thick layer of dust. The scientists faced a difficult task, but they are doing everything possible to solve it, relying on the composition of the environment around the star in the distance. This way, we can at least get approximate data. And now, we are finally getting to the question of which star is currently considered the largest in the universe. And now the leader is WOHG 64. It belongs to the red supergiants. The star is located in the Large Magellanic Cloud, 160,000 light-years away from our planet. WOHG 64 is about 1,540 times the Sun's radius. If you place the star in the solar system, it would reach as far as Jupiter's orbit. It is believed that WOHG 64 has almost completely exhausted its nuclear fuel, so it is in the final stages of stellar evolution. This explains the star's enormous size. There's also a torus-shaped dust cloud around WOHG 64. Its diameter reaches 1 light-year. The cloud is mostly made up of material that the star has expelled during its life cycle. If all the accumulated material from the cloud were used, it would be enough to create 9 copies of the solar system. It seems the situation is now completely clear. So we know that WG64 is the largest star in the universe, right? Actually, it's not that simple again. Most likely, WOHG 64 isn't the largest star. There have been other studies that concluded the actual size is quite different. So the situation is still pretty unclear for us. However, we do know for sure that there are many giant stars in the universe. But at the same time, we still can't determine which one is the largest. We just don't have enough data, knowledge, or technology. Things may change in the future. Under the boundless sky, framed by mysterious charm, we feel like tiny particles in the vast universe. All these enormous stars, whose mysteries we try to unravel, are like mysterious torches illuminating the path into the uncharted depths of the universe. In every twinkling star in the night sky, there are unfathomable secrets and potentials hidden. Despite all our efforts, the world of stars remains full of mysteries and enigmatic anomalies, which draws us even closer to it and calls us to further study and immerse ourselves in its boundless expanses. Every new step in our understanding of the nature of the cosmos is a step toward understanding our place in this amazing world and discovering new horizons of knowledge. The intertwining of stellar mysteries and human striving for knowledge leaves us searching for answers that shine like stars in the endless darkness of the universe. And what do you think? How soon will we find out which star is the largest in the universe?